Please wait, I'll be starting within 2 minutes. Some of your friends haven't joined yet, so let them join. Then I will start the class. Good morning, students.
Good morning, ma'am.
Good morning, ma'am.
Good morning,
Yes.
ma'am.
Good morning, everyone. Let me share the screen of today's class. Is the screen visible to all of you?
Yes, ma'am.
Yes,
Okay. We were discussing module number 3, transformer. So as of now, we have studied the basic definition of transformer, the basic working principle of transformer, the block diagram of single phase transformer, different types of transformer, and then we have studied preliminary things about ideal transformer action, its equivalent circuit and phasor diagram, and the non-ideal operation or the basic concepts of practical transformer. So if you have any queries from transformer, what you have studied, you can ask me now, because today I'm going to start with the working principle, equivalent circuit, and phasor diagram of practical transformer. And also we have seen two basic losses, the core loss and copper loss. Core loss mainly includes two types of power losses like eddy current loss and hysteresis loss. These losses are actually absent in the operation of ideal transformer. There is no concept of these losses in ideal transformer because ideal transformers are totally loss-free transformers. Okay. So this is the circuit, equivalent circuit as well as phasor diagram that I was discussing in the last class. This is actually the no-load circuit model of a practical transformer, right? It includes two major components like RFE and XM, where XM is the magnetizing reactance and RFE is the resistance that represents the losses. So basically, these two components are not present in the equivalent circuit of ideal transformer. Okay. And what is this basic phasor diagram? This basic phasor diagram at no load operation of transformer can be understood by the fundamental transformer voltage equation. Now, considering phi or phi m as the reference vector, as you can see, the voltage, the input AC voltage Vt is always leading by this mutual flux. Why? Because this input voltage Vt is responsible for the production of the induced EMF at the primary winding by Lenz's law, by Faraday's laws of electromagnetic induction. And this EP is nothing but the induced EMF at the primary winding. So this should be lagging by the mutual flux that we have derived already. Why EP is lagging by 90° by the mutual flux. Here flux is alternating. So if you consider flux phi equals to phi max cosine omega t, then definitely induced EMF EP at the primary side by following Lenz's law or Faraday's law will be expressed as ddt of phi. So ddt of phi max cosine omega t is nothing but sine omega t. It's sinusoidal function which will be obviously 90° lagging by the cosine function. So that's why EP will be lagging by phi, but by Lenz's law, obviously EP will always oppose the primary input voltage Vt. So Vt will be, the vector Vt will be 180 out of phase with EP. Now coming to this I naught. What is I naught? This current, the no load current. This is called no load current. So this is the transformer primary current at no load. And this will be equal to summation of these two currents for practical transformer only, for non-ideal transformer only at no load. That means the secondary side is not connected with the load. Okay. So here definitely Im is the magnetizing current will be always in phase with phi. Why? Because this magnetizing current is only required to magnetize the core. We'll see that later. Why the core needs to be magnetized always. What will happen if the core starts to demagnetize itself? What will happen in the working of transformer? So it is always desired to make the core magnetized, right? So this magnetizing current is required for both type of transformers, for ideal transformer and practical transformers as well. Now here in case of non-ideal transformer, what happens along with this magnetizing current which is in phase with phi, there is one more component which is called the core loss component current, IFE. And this is required to supply the core losses only. So it will be flowing through the path having the resistance which is just in parallel with the magnetizing reactance XL and is denoted by RFE. Okay, so this amount is very, very small. If you look at this phasor diagram minutely, you will see that for ideal transformer, basically this IFE component is 0. That's why in case of ideal transformer, the vector I0 is almost in phase with Im or phi. The magnitude of this Im, the magnetizing current, is very, very high compared to this IFE, the amount of current providing the core losses in case of practical transformer, right? So if you take these two vectors, IM and IFE, you will get the resultant one by the triangle law, which is the no load current I0. Now we'll see the detailing of this phasor diagram in the working of practical transformer or the actual transformer. These are the parameters can be obtained from the no load circuit model, like the component IFE, IM, right? The no load current, which is just the sum of these two currents, core loss current and magnetizing current.
Ma'am,
So, yes,
ma'am, the magnitude of IFE is very less, ma'am, compared to IM.
IM, yes, right.
Uh,
This,
Ma'am,
this,
why does that happen?
yes,
Oh, ma'am, why is it less than IM?
it is assumed very, very less because this current is actually supplying the core loss, and our objective is to reduce the core loss always,
Oh, okay,
right?
ma'am.
We'll never expect more core losses in the working. We'll design the transformer in such a way that these core losses are less. That's why we'll assume that this IFE is less. And actually, in practice, the IM is highly required. Why? This is the magnetizing current, always required to magnetize the core. But this current is not required actually. But
Yes,
we cannot avoid this current also in practical transformer, because in practical transformer, in actual transformer, there are many more parameters which are dependent on the working the principle of transformer action. So this is unavoidable. This IFE is unavoidable. So we'll assume, we'll consider very small portion compared to IM. Now IFE can be calculated as VT by RFE. Definitely VT is the voltage across this register. You can see from this circuit model, VT is the voltage across this IFE. Across RFE, the resistance, and IM can be calculated as VT by J of XM, right? It's flowing, IM is flowing through the reactance, so definitely you have to consider this J operator, J of XM, and the total current I know, the low load current I0 is sum of these two currents, IM and IFE. So these are other parameters can be obtained from the no load circuit model, XM, RFE, PFA, etc. And definitely the apparent power SM can be calculated as VT times I0. And both the values are definitely the RMS values. Now coming to the actual working of practical transformer, it's totally different from ideal transformer. How the practical transformers are different. One is the effect of permeability. Second is the concept of eddy current loss, hysteresis loss. Third is the concept of leakage fluxes. Fourth is the concept of finite winding resistances. Like in ideal transformer, actually, we assumed the infinite permeability. Infinite permeability means permeability is infinity. Permeability is equal to infinity. That means entire flux, whatever will be generated by Lenz's law, whatever will be generated by the input voltage, supply alternating voltage, will be totally confined within the core. Okay, but in practice, it is not possible. It is not possible to keep all the flux generated within the core itself. So some of the flux will be definitely uh, linked with air. Okay, now look at this block diagram as shown in this slide. Here, it's basically the a schematic of a core type transformer. Core type transformer signifies that the windings will be mainly wrapped around the core. This is actually the core. Okay, and these are called limbs. So the primary winding is wrapped around the first limb, and the secondary winding is wrapped around the second limb. N1 and N2 are the number of turns associated with primary and secondary windings, respectively. And what is phi? Phi is the flux flowing through the core material, and this flux will be generated because of the alternating voltage, right? Now, in transformer operation, the energy transfer will be taking place because of the mutual flux, which is only confined within the core, which is only linked with both the coils, both the primary and secondary coils. Right? In ideal transformer, we have assumed that the permeability of the core material is very, very high. Mainly, this type of core made up of steel or any steel alloy whose permeability is near about 1500, whereas the permeability of air is only 1, right? So this type of iron core or steel core will allow the core to carry 1500 times higher than that of the air. So more flux will be confined within the core if it is made up of high permeability material. But in practice, actually, what happens? Some of the flux will be also linked with only either with the primary coil or with the secondary coil. Like this is the flux. Just follow my cursor. This is the flux which is confined within the core, which is actually this flux, the mutual flux. And this mutual flux is only responsible for transferring the energy from one circuit to another in transformer operation, right? That's why we mainly concentrate on this flux phi max or the mutual flux. This is the useful flux. But sometimes what happens, some of the flux lines are also linked with either with only the primary coil or with only the secondary coil. These are called the leakage fluxes. Okay, and these leakage fluxes are not the useful fluxes. That means these fluxes are not used. This cannot be used for the transfer of energy from one coil to another coil. Energy can be only transferred from primary circuit to secondary circuit via the mutual flux, which is confined only within the core. Is it clear to everyone? Why the leakage
Yes, ma'am.
fluxes are not desired in transformer operation? But it is also true that in the working of practical transformer, we cannot avoid the presence of these leakage fluxes. So that's why to compensate these leakage fluxes, always we need to provide some finite value of winding reactance. Like these leakage fluxes will be compensated by the transformer winding reactances, right? And transformer windings are mainly constructed with copper materials, as I said earlier. So definitely, because of these copper windings, there will be some ohmic drop. Whenever current will be flowing through these resistances or through these copper windings, there will be some copper losses or ohmic drops within the winding. So these are not avoidable. The concept of this leakage flux, the winding resistance concepts, these are not avoidable in practical transformer operation. And because of the presence of these losses, along with the core losses, definitely the hysteresis loss and eddy current losses, which will be generated within the core, depending upon the core material, depending upon the BH characteristics curve that I'll explain later, the effect of core material, the effect of BH curve, the effect of saturation point in the open circuit characteristics curve, these along with the permeability concept. Because in practical transformer, definitely the core material will have some finite permeability. What is the meaning of this finite permeability? In case of ideal transformer, this is infinite. No flux can be leaked through from the windings. There are no leakage fluxes in the ideal transformer working. But in practical transformer, these permeability has some finite values. That means some flux, some portion of main flux or the mutual flux can be leaked through from the winding. Okay, can be linked through either with the air or through the winding itself. So that will generate whenever flux is linking with a particular coil, with only one coil. What is the meaning of that? There will be definitely a voltage will be induced, that is called self-induced EMF. Here we are dealing with mutually induced EMF in case of transformer operation, because here the secondary coil is basically linked with the first coil, the primary coil. That means this E2, the EMF induced at the secondary winding, is definitely the EMF induced because of the primary induced EMF. So there is a mutual coupling between the two windings. But other than this mutual inductance, if you know the concept of magnetism and the difference between self-inductance and mutual inductance, will be able to understand what I'm trying to say, that coil, if a current is flowing through only one coil, then there will be a question of self-inductance. There will be a chance of production of self-induced EMF when an alternating current is only linked through a single coil. Are you getting it?
Yes, ma'am.
Okay, so these not sorry, these leakage fluxes are basically uh, at the cause of the generation of self-inductance, right? And these self-inductance will be actually represented as the magnetizing reactance in the equivalent circuit of transformer. That I'll explain later. Okay, so because of these factors, right, the permeability is not infinity in case of practical transformer, right? It has a finite value. That means all the main flux will not be confined anymore within the core. Some of the flux will be used as the leakage flux. So because of these, definitely the practical transformer operation will be something different from that of the ideal one. Now look at the phasor diagram. These two are phasor diagrams at no load condition and at loaded condition, respectively. Okay, so you are familiar with the no load phasor diagram. Considering phi, the main flux or the mutual flux, as the reference vector, I in the magnetizing current will be in phase with that phi, and the terminal voltage V1 and V2. Terminal voltage V1 means the input voltage, alternating voltage, and the voltage uh, across the secondary winding is V2. Both are 90-degree, leading by the flux, and the induced EMF at the primary winding as well as the secondary winding will be lagging by the mutual flux by 90-degree. That I have discussed already. So this is E1 and this is E2. Right? Always V1, the input voltage will oppose the primary induced EMF E1, and the secondary voltage V2 will oppose the secondary induced EMF E2. Right? So here is the V1. This is E1 induced at the primary winding, and this is E2 induced at the secondary winding because of the mutual flux pi max. And if the secondary side is connected with a load, then definitely a voltage V2 will be developed because of the secondary current I2. And here two dots are shown in this figure, representing that the two currents I2 dash marked over here and I2 both are entering to the coil at this dotted position. Okay, both the currents are entering the coil. That's why we have considered two dots over here at the entry terminal of the two coils, in order to represent the path by which actually the two currents are flowing through the winding. Okay. Now, actually, what happens in transformer working, in practical transformer working. Look at this phasor diagram. When the secondary side is getting loaded, and there is a load across the secondary side. This is phi, the mutual flux, taken as the reference vector. These two are already understood, E2, E1, V1, V2. Right? Im is the magnetizing current, will be in phase with phi. Right? And what is the no load current? What is the no load current? No load current is somewhere here. I naught. What is I naught? It's just the resultant of magnetizing current and the loss component of the primary current. The current component which is supplying the core losses only, IE, mainly denoted as IE. So the resultant of these two vectors, IE and IM, is I naught, the no load current, right? That means when the secondary side is not connected to any load. Now, when the secondary side is connected to the load, what happens actually? What happens? Secondary current I2 will be flowing through the secondary winding, right? And this is your E1, this is your E2, and say this is your V2. This is your V2, right? Ideally, E1, E2 and V2 actually are out of phase by each other. But practically, when the secondary side is loaded, what happens? Considering the lagging power factor type load or considering the inductive type of load, what happens? Current, the load current, the secondary current will be lagging by this secondary terminal voltage across the load by the angle theta. Okay, this is the voltage across the load now, which is not in phase with E2, which is not in phase with E2. Why? That will be understood from the equivalent circuit later on. But for the timing, you just try to understand that this is the practical transformer, right? So in practical transformer, we need to consider the winding resistance, the winding reactance, etc. That means definitely in the secondary winding, there will be a concept of secondary ohmic drop and secondary reactive drop because of the resistance, winding resistance and the winding reactance. Okay. Now, due to that, definitely V2, the voltage across the load, if a load is connected over here, will not be equal to this induced EMF, E2. There will be definitely a difference between V2 and E2. And that difference will create this angle between the two vectors. Right? Depending upon this voltage, V2, the current through the load, through the secondary winding, will be taking its position, and considering inductive type of load, the lagging power factor type of load, definitely this vector I2 will be lagging by the voltage V2. Now, in transformer operation, always the secondary current, all the secondary current or secondary volt amperes must be compensated by the primary volt amperes, right? We have already learned that V1 I1 is always equal to V2 I2, the fundamental EMF equation of a single phase transformer. Or we can say that V1 by V2 is equals to N1 by N2 is equals to I2 by I1 equals to small NC turns ratio. Right? That means I1 N1, the primary ampere turns, should be always compensated by the secondary ampere turns, ideally, neglecting all types of losses. Right? So basically, this I2 vector must be compensated by this I2 dashed vector. But this I2 dashed is not the primary current. This I2 dashed is not the primary current. What is the primary current? Primary current is I1 here. Now, what is the source of this current? I1. The actual primary current is I1. But to satisfy the transformer working, to satisfy the basic EMF equation, the secondary current, all the secondary current I2 must be compensated by the primary current I2 dashed. Okay. Now, how to obtain this primary current I1? Actually, what happens whenever there is a load at the secondary side? What will happen? Secondary current I2 starts flowing through the winding. Consequently, what will happen? There will be a voltage developed across the load. Right? Now, this voltage V2 will indirectly try to reduce the flux phi, because this V2 will generate because of this E2, the induced EMF across the secondary winding. Right? But always this V2 will oppose the cause of it by Lentz's law. That means V2 will always oppose E2. If V2 opposes E2, what will happen? E2 will indirectly oppose the cause of it. What is the cause of production of E2? The main flux, mutual flux. Now, indirectly, V2 will reduce the main flux, that is phi m, within the core, which is not desirable. Okay? Because in turn, flux will try to reduce the EMF induced at the primary side, E1. And E1 will further try to reduce the cause of it by Lentz's law, which is I1, which is not desirable. Because I1 is the main current drawn by this voltage. This voltage is fixed. This is not. This cannot be varied automatically. Right? So somehow the working of transformer is getting hampered because of the load across the secondary winding, which is not desirable, which is not possible at all. Now, how to overcome this problem? Because this working will be, sorry, the working of the transformer operation is a continuous process, right? Now, somehow the current needs to be compensated, right? The reason because of which the flux, the main flux within the core is trying to reduce down, that cause must be compensated by automatically drawn some more primary current from the input source. What I'm saying, actually what happens whenever there is a chance of reduction of this E2 because of this V2, there will be definitely a difference between this V2 and E2, right? And basically this difference cause the transformer winding to draw more current from the input side. Are you getting this? What is V1? What is V1? V1 is equals to, for practical transformer, plus I1 Z1. What is it? The impedance. What is this impedance? Say this is the primary winding, having the primary winding reactance X1 and primary winding resistance as R1. So what is the impedance of the primary winding in total? That is Z1. And what is the current flowing through this primary winding? So for example, it is I1. So I1 Z1 is basically the drop across the primary winding. So in practical transformer, this voltage will no longer be equal to only E1, the induced EMF. It is minus of E1 plus I1 Z1. Right? So because of this, and also the same, by applying the same principle here, V2 will be definitely equals to E2 plus the drop I2Z2, right? The voltage generated across this winding plus the drop, not plus, E2 minus I2Z2 is equals to V2, right? The whatever losses will be generated because of the winding impedance, that must be subtracted from the EMF generated at the secondary winding in order to obtain V2, the terminal voltage across the load, right? So these two fundamental equations are responsible for the automatic control of the primary winding current. Okay. So this current vector I1 from this phasor diagram can be expressed in terms of this actual current I2 dash that is to be produced in order to compensate the actual secondary current and the no load current. We have this no load component of current I0, right? And we have this actual vector I2 dashed, which is to be always out of phase with the secondary current vector I2 to satisfy the transformer working principle. Now, considering these two vectors, this new vector will be generated, that is called I1. This is called the primary winding current. This is called the primary winding current, the actual primary winding current under the loaded condition of the transformer. Okay, is it clear to everyone?
Yes, ma'am.
Okay. Now look at the equivalent circuits. So the first is the circuit when the secondary is open. You can follow the switch which is open here. This is the secondary load actually with the impedance Z2. And what is I2? I2 is the secondary current, which is definitely zero because the path is not complete and no load is connected. So no secondary current will be flowing. And this is the input voltage V1. So when no load is connected, definitely the primary winding must draw from the input voltage in order to magnetize the core always. So here only a current required, which is IM, the magnetizing current, which is just equal to I1, the primary current. And as I said earlier, that this current is very, very small, almost 2 to 5% of the rated current of the transformer. Only a small portion of primary current is required to magnetize the core only. And to flow this magnetizing current, we need a path to incorporate within the circuit, and this path will be represented by this coil having the inductance, having the reactance XM. Okay. And I2 dashed is here 0. I2 dashed is here 0, right? Because no secondary current is required here. No secondary current is required. So I2 dashed is 0. Okay. And because I2 is 0. Is it clear to everyone? What is I2 dashed? I2 dashed is the current vector at the primary side, which is to be there to compensate the total secondary current I2 at no
Yes,
load
ma'am.
operation, right? At no load operation, I2 is not present. So definitely there is no requirement of I2 dash. So in this figure, we'll mark I2 dash as 0. Okay. Now when the secondary side is connected with the load, when this Z2, the load, the lagging type load, definitely inductive type load is connected, what will happen? So there will be a question of the current I2 dashed. So this I2 dashed, you can see from this figure, it is just sum of I1 and IM. I1 and IM. Look at the phasor diagram. What is I1? This is I1 and this is IM. Right? or indirectly you can say that I1 is basically dividing into two parts, IM and I2 dashed, right? I1 is the resultant of I2 dashed and IM. What is IM? The magnetizing current. Considering the loss is very, very small. Considering the loss is very, very small, that means almost it is the case of ideal transformer, right? So in ideal transformer, the value IFE, the loss component of current, is very, very small. So neglecting this component only, we have IM that will be marked over here. So IM plus I2 dashed is just equal to I1, the primary current. That means the no load current I0 is almost in phase with IM. Clear? So this is basically the case of ideal transformer. Now two more new terms to be incorporated here. The equivalent circuit referred to primary and referred to secondary. Right. So I have added one table showing all necessary formula to be remembered always when you'll be going to draw the equivalent circuit, because this equivalent circuit is this concept is very huge in transformer. In many ways, a transformer equivalent circuit can be drawn. So one needs to understand these things very clearly, that when to apply the equivalent circuit referred to primary, and when we are referring primary side, how the parameters, the important parameters will be expressed. So for the time being, you just try to learn that when we are referring the primary side, right, this will be marked as S squared Z2. A is the turns ratio, N1 by N2, right? And when we are referring a secondary side, then the primary voltage will be represented as V1 by A instead of V1. Are you getting this? For referred to primary, the secondary voltage V2 dashed will be represented as A squared Z2. But when we are referring it in terms of secondary, then primary voltage will be referred as V1 by A. This reactance Xn will be referred as Xn by A square, because the secondary voltage is now V2. Secondary current is now I2. Now considering the core loss into account. How to determine the equivalent circuit for ideal transformer, considering the core loss. Previously, we have not considered the core loss, only we have considered the magnetizing current. Right? Now, if the core loss is there, though it's a ideal transformer, if there is core loss, small amount of core loss, then what will happen? Now we need to draw a resistance in parallel with this reactance, RE1. RE1 will supply the core loss. So definitely IE1 will be current flowing through this. And because of this current I1, E1, this vector will be generated, which will generate the no load current I0 further. See, this is the no load current I0. Now this time I1, the main current drawn by this primary winding, is equal to the current I0 plus the current which is actually flowing through the winding. See, here it is marked as I2 dash. Now it's clear to everyone why I1 is divided into two halves. One is I0 and I2 dash, what I have described in this phasor diagram.
Yes, ma'am.
Okay. Now this is the case where we are referring the primary side. So when we're trying to draw the equivalent circuit referred to primary, these things we need to taken care of, these expressions. And when it is referred to secondary, we need to taken care of these things. These formulas are fixed. See, at last, at the end, yes. Here I have, yes, included this slide, so that you can remember always that what is the actual impedance on the secondary side referred to primary. The actual impedance at the secondary side is Z2. But when we are trying to draw the equivalent circuit referred to primary side, it will become S square Z2. When it is referred to secondary, it is Z1 by A square. So based on these two impedances, actually we can derive the voltage from secondary to the primary as V2 dash equals to AV2, and voltage from primary to the secondary as V1 dash equals to V1 by A. Okay. And considering these two expressions of voltages V1 dash and V2 dash, further we can derive I1 dash as A times I1, I2 dash as I2 by A. A is the turns ratio, number of primary turns divided by number of secondary turns. So you need to remember these 6 formula always while we are trying to draw the equivalent circuit. Okay. So this is the equivalent circuit considering core loss to account. Now considering the both the core loss and magnetizing current. This is the case at no load. When no load is connected, only we have the no load current I naught, which is the summation of the two currents, magnetizing current and the core loss current I1 or IC1. And this is the phasor diagram with load. When load is connected, so definitely this lower portion is not drawn here. When load is connected, load current will be flowing I2. That must be compensated by this current I2 dash that should be flowing through the primary winding. But actually in primary winding, which current is flowing? I1. What is I1? I1 is just the summation of this I2 dash and the no load current I0. See, this is I0, which is the summation of E1, the core loss current, and the magnetizing current IM. And this is the current, the actual current to be flown through the primary winding in practice, neglecting all the losses. So the resultant of these two currents, I2 dash and the no load current I0, will get new current vector I1, which is the actual primary flowing through the practical transformer. This is E1. Mathematically, that should be lagging by 5 by 90. And since the transformer is practical type, the terminal voltage V2 when load is connected will be lagging by this induced EMF across the secondary winding in order to satisfy all types of losses within the winding. And this is angle between the load voltage and load current, considering lagging power factor type of load. Is it clear to everyone? Have you all understood the difference between ideal and practical transformer in
Yes.
along with equivalent circuit and phasor diagram?
Yes, ma'am.
Yes, ma'am.
Okay. What is the time now?
12:20.
It's 12:20. Okay. So next day, we'll start with this equivalent circuit of a practical transformer, considering the concept of leakage flux. Today, you have understood a little bit about this leakage flux. In this diagram also, I have drawn leakage flux. You can see leakage flux is the flux which is actually flowing through one coil. And these are not the useful flux. The mutual flux is the only flux required in transformer operation in order to transfer the energy from primary winding to secondary. So these leakage fluxes indirectly will create the effect of winding reactance. Right? So this is the actual equivalent circuit of ideal transformer. Here I have shown in this slide, showing all the primary and secondary side components. R1, X1 at the primary resistance and reactances. R2, X2 are secondary winding resistance and reactances. See, now you are aware of these components, RE1 and XM, the magnetizing current and the core loss component of current. And this will be only drawn across the primary side because these terms are related with the primary side only, because these two components will be generated at no load operation only. Also in a loaded condition, they are required, but actually these two factors are related with the primary current, primary winding current. That's why these two components will be drawn the primary side. Okay, and this XM and IM is always required to magnetize the core, always. And you are E2, you know, the primary winding induced EMF and secondary winding induced EMF respectively. Okay, and also you have understood the phasor of I1 and I2 dashed and the no load current I0. This is I0. Right? So next day we'll start from this, once again, from this equivalent circuit, both refer to primary and refer to secondary along with the mathematical equations. Okay, do you have any questions up to this which you haven't understood from today's class?
Ma'am, in the last slide, ma'am,
Yes.
ma'am, that theta angle, ma'am, in second last slide, before this.
In this slide?
No, ma'am, before this also. In this slide, ma'am, the theta angle, ma'am, what does it correspond?
This theta?
Yes, ma'am.
This theta?
Yes, ma'am.
This is the angle between the load voltage and load current. V2 is load voltage, I2 is load current.
Yes, ma'am.
As the load is inductive type, lagging power factor type, the load current I2 will be always lagging by the load voltage V2.
Okay.
Okay.
Yes.
Okay, so here I2 is lagging by V2 by angle theta.
Okay.
If you consider a pure inductance as the load, then definitely this angle will be equal to 90 degree. But it's not a pure inductive load. Definitely some impurity will be there as resistance. So this angle will be lesser than, slightly lesser than 90 degree.
Okay, ma'am.
Okay.
And the
So
power
this
factor angle here is theta 2
power factor.
angle.
Power factor angle can be used in both ways. This theta can be also called as power factor angle. And that power factor will be actually called as load power factor. And what is this theta 1? Theta 1 is angular difference between primary current and primary voltage. So this angle will create a power factor at the input side. And what is this theta 2? This theta 2 is the voltage difference between, see, the voltage V2 and the current I2. So basically
Right.
this theta and theta 2 are same.
Yes.
No, not same. The theta 2 is the angle between V2 and I2 dashed. I2 dashed. I2 dashed means the current in the primary.
Across load.
Yes. No, I2 dashed is the current in the primary, neglecting all types of losses.
Yes, ma'am.
Right? That means ideal transformer. So for ideal transformer, the angle between the secondary current and the secondary voltage is theta 2. But in practice, it is theta. Because for practical transformer, the primary winding current is I1, not I2 dash. So all these can be expressed as power factor angle. Just you have to identify how these angles are made.
Yes, ma'am.
Okay.
Understood.
Okay. Let me stop here. Please wait. Quickly, I'll be taking your attendance. Rule 1.
Present, ma'am.
2.
Present, ma'am.
3.
Present, ma'am.
4.
Present, ma'am.
5.
Present, ma'am.
6. Riddhi. 7. 8. 9.
Present, ma'am.
10. 11.
Present, ma'am.
12. 13.
Present, ma'am.
14.
Present, ma'am.
14. Shadnik Bishas.
Present, ma'am.
Okay.
Hello, ma'am. I'm 8, ma'am. Opposite.
Ma'am, 12 present.
12 and opposite 9. Okay.
No, opposite
Next,
is 8.
15.
Present, ma'am.
Yes. Who was talking?
15, ma'am.
15. Yes. 15 I didn't call. Abir.
Yes, ma'am.
16,
Yes, ma'am.
17,
Yes, ma'am.
18,
Present, please, ma'am.
19,
Present, ma'am.
20,
Present, ma'am.
21,
Present, ma'am.
22,
Present, ma'am.
23,
Yes, ma'am.
24,
Present, ma'am.
25,
Present, ma'am.
26,
Present, please, ma'am.
27,
Present, ma'am.
28,
Present, ma'am.
29, Harsh, 30,
Present, ma'am.
31,
Yes, ma'am.
32,
Present, ma'am.
33,
Present, ma'am.
34,
Present, ma'am.
35,
Yes, ma'am.
36,
Present, ma'am.
37,
Present, ma'am.
38,
Present, ma'am.
39,
Present, ma'am.
40,
Present, ma'am.
41,
Present, ma'am.
42, Orgodeep, 43,
Present, ma'am.
44,
Present, ma'am.
45,
Present, ma'am.
46, 47,
Present, ma'am.
48,
Present, ma'am.